Woo! All right. Ladies and gentlemen, welcome back to section 4.6. We are talking related rates one more time and for the final time. So let's get right to it. Example 1 here. This is a really good practice question. I would highly encourage you to try to set up and do this one on your own. Pause the video right now, read through the question, then come back and take a look at the work that I do here. Okay, let's talk about this. A police cruiser approaching a right-angled intersection is chasing a speeding car that has turned the corner and is now moving east. When the cruiser is 0.6 miles north of the intersection and the speeding car is 0.8 miles to the east, the police determine with the radar that the distance between them and the car, the speeding car, is increasing at 20 miles per hour. If the cruiser is moving at 60 miles per hour at the instant of measurement, what is the speed of the car? Okay, really good practice question here. And so one little piece of advice in a question like this is I want you to think of this as kind of like a Google Maps type of view, right? You are looking from the top down onto this high-speed chase, okay? Now, we know the cruiser is 0.6 miles north of the intersection. The speeding car is going to be to the east of that intersection. And so that's going to give me a right triangle like this. And so I'm going to go ahead and label a couple of things here. Okay, so I'm going to put my PC, my police cruiser, right here. And it is going to be approaching the intersection. And meanwhile, my speeding car is to the east and it's running away from the intersection. Okay. And so, comparing this to the last note sheet real quick, right, where we had that hot air balloon question, right, that question was talking about angle of elevation and a rate of change that was in radians per minute, right? Those were some hints that we were using a trig equation here, right? Here, we don't have anything involving angles, right? And so if we have nothing involving angles, right, then what else do we normally do with the right triangle, right? Let's talk about good old Pythagorean theorem. Okay, so I'm going to label this distance x between the speeding car and the intersection. The police cruiser to the intersection is going to be y, and the direct distance between the police cruiser and the speeding car I'm going to call z, which is going to serve as the hypotenuse here. Now, I'm not drawing out like a full, road here, but if you kind of want to think about like where the road would be, right? We're kind of like doing something like this, and you put the yellow lines in the middle, right? That's kind of like what the road is. So I've kind of, simplified the picture here to the core part of this, which is the right triangle, right? That's the thing we want to focus on, right? That's kind of like the whole intersection, though. If you really want all of that in your picture, it is not needed, though, okay? We want to focus on the right triangle, all right? Okay, let's look for some rates. So, police cruiser is approaching the right-angled intersection, right? That's important. The speeding car moving straight east, that's important. We're going to come back to these distances here in a little bit. I want to talk about the rates. So we know the distance between the police cruiser, and the speeding car is increasing at a rate of 20 miles per hour. And so that 20 miles per hour is going to represent the z in my picture. dz dt is going to be 20 miles per hour, right? That's the direct distance between the police cruiser and the speeding car. The cruiser is moving at 60 miles per hour at the instant of measurement. So that's my police cruiser, our boys and girls in blue. 60 miles per hour, that's going to be y in my picture. So that's going to be 60. And now it says, what is the speed of my car, right? My speeding car. I do not know its speed. And so I'm going to call its rate of change dx dt, which I do not know and am solving for. Okay, so that's my setup here, right? And so that's the three rates that I want to relate. Now, if you think back to the last video again, that last question we did with the conical tank, I was very anti three variables. But in this case, three variables, three rates of change is going to be fine because that's how the Pythagorean theorem rolls. So we're good to go with that. Okay, now there's something very important I want to talk about here before we get going. Okay, one of my rates is wrong. What? How could this be? Which of my rates is incorrect? dy dt or dz dt? Okay, and I'll let you think about this for a second. All right, and here's something I want you to think about. Okay, my police cruiser, right? It is approaching the intersection. So if I kind of think about this cruiser over time, so at the moment I'm measuring, it's over here, right? And then it's going to get closer and closer to my intersection, right? Whoops, auto scroll took it past there, until eventually it's going to reach that intersection. At the moment it reaches that intersection, what would y be? Y would be 0, right? Because you have to look at what your variables represent. Y in my picture represents the distance between the police cruiser and the intersection, right? So what's happening to Y as my police cruiser goes about on this chase, right? What's happening to Y? Y is getting smaller, okay? And therefore, I need to make dy dt be negative 60. Okay, now I have to clarify something very important here. That does not mean my police cruiser is driving in reverse or going backwards or anything like that, right? What's happening here is that dy dt is not necessarily the same thing as the speed of the police cruiser, okay? You can kind of think back to chapter 3 when we talked about velocity and speed, right? Remember, speed is always the absolute value of the velocity, right? Speed is always positive. So when you're looking at the speedometer, if you're the police officer and your cruiser, you're looking down at the speedometer, it's going to say 60, right? The reason I have to make this negative 60 is because of what y represents in my picture. Y is the distance between the cruiser and the intersection. And if this cop is doing his or her job, that distance should be getting smaller, right? And so I represent a variable that's getting smaller by putting a negative in front of its rate of change, okay? dy dt has to be negative 60, and you're going to see this play out at the end here, okay? All right, so let's relate x, y, and z, right? Let's go to my oldest friend, the Pythagorean theorem, x squared plus y squared equals z squared, okay? And I will take the derivative of this with respect to time, so I will go dt here, okay? And so that is going to give me 2x dx dt plus 2y dy dt is going to equal 2z dz dt. These Pythagorean theorem questions are great because you're going to get easy derivatives, right? Things squared. That's just good old power rule, okay? And now something else really nice is going to happen here, right? I can divide out a 2 from all of this. So I'm just going to cancel out those 2's and ignore them, okay? And now we can go ahead and plug everything in. And now we haven't really talked about this yet, but what are the values of x, y, and z? Well, let's look back here. When the cruiser is 0.6 miles north, right? Distance between the cruiser and the intersection at this moment is 0.6. So that's my y. The speeding car is 0.8 miles to the east, so that's going to be my x, 0.8. And now we can think back to our Pythagorean theorem here. If x is 0.8, y is 0.6, some of you might be able to do this in your head. If you can, that's great. You're going to save yourself some time. But if not, do the work, people. Write it out, okay? Pause the video, write it out, solve for z, okay? But if you remember, a little helpful hint here, we're talking Pythagorean theorem, right? Let's not forget Pythagorean triples, right? 3, 4, 5. How about 6, 8, 10, right? I can divide all of those by 10 and get 0.6, 0.8, and I can get 1 for z, right? So at this moment, again, what does z represent? The direct distance between the cruiser and the speeding car is exactly 1 mile. Okay, so we can figure out the value of z by taking my givens and plugging them into the Pythagorean theorem. Now, what are we trying to do here? Dx dt, that's what I want to solve for, right? Don't know what the speed of the speeding car is. We're going to try to figure that out. Dy dt has to be negative 60. Has to be. Okay, dz dt, we know that's 20, right? Which also tells us something important, right? If a rate is positive, then the variable is getting bigger, right? So that means, unfortunately for our boys and girls in blue, the speeding car is is getting away from our police cruiser in this scenario, right? Because the rate of change of the distance between them is a positive number, okay? Okay, so what's going to happen here, right? I'm going to have 0.8 dx dt. 0.6 of 60 is 36, but it's a minus, so I will subtract it. 1 times 20 is 20. And now, here's why that negative was so important, right? If you would have left that as a positive, right, then you would have positive 36 here. You would have subtracted it over, and you would have gotten negative 16, where you should have gotten 56. 0.8 dx dt should equal 56. Okay, and so last step, divide by 0.8, and so we get dx dt is 70 miles per hour. Okay, now again, let's come back up to the negative 60. Had that been a positive, you would have gotten positive 36 here. Subtracted it from 20, you would have gotten negative 16. So your dx dt would have been negative 20 miles per hour. Now, you can take that negative 20 and go, hey, the question's asking for speed, right? So let me just make it positive 20. But if dx dt is a negative, that means that the speeding car, right, would be approaching the intersection, right? That's a real dumb criminal, right, if they're going back towards the police. Okay, so even if you were to write a positive number for your final answer, it still doesn't make sense for dx dt to be negative, right? My speeding car is going east, right? It's getting away from the intersection, okay? So you have to pay attention to the context in these questions, okay? Now that you've seen this first example, I think example 2 is definitely one that you could take a look at on your own. So this is another good opportunity for you to pause and try this example on your own, and then come back and compare it to the work I'm about to show you. Okay, so example 2, an 8-foot ladder is leaning against a wall. The top of the ladder is sliding down the wall at a rate of 2 feet per second. How fast is the bottom of the ladder moving along the ground at the point in time when the bottom of the ladder is 4 feet off the wall? Okay, so I have a picture drawn here, right? We have our ladder set up here. I'm going to put a couple of variables into this picture, right? This is going to be y, this is going to be x at the bottom, and now here is my ladder, which I will call z, okay? But before we do anything, I want you to think about something really important, okay? Which of my variables is not going to change, okay? Keep it simple. pretend like this object doesn't have extendable versions, right? Keep it simple and realize that the ladder is always 8, okay? Now, if you really are dying for more variables here, you can leave it z, but you have to recognize then that its rate of change has to be 0, okay? If you insist on doing it this way, right, you have to make sure you understand that its rate of change is 0. I'm going to not deal with additional variables and rates of change when I don't have to, because I know that the length of this ladder is not changing in this scenario, okay? So let's think about the motion here, right? The top of the ladder is sliding down the wall, right? Sliding down the wall, and so that's going to kick the base of this ladder out to the right, okay? So let's look back at what we are given, right? Top of the ladder is sliding down the wall at a rate of 2 feet per second. So that's going to correspond to dy dt. And again, this has to be negative, right? Because y is representing the distance between the ladder and the ground in my picture, and that distance is going to get smaller. I want to know how fast is the bottom of the ladder moving along the ground. And so that is represented by x in my picture. And so I am solving for dx dt. And that is what I want to relate. Okay. And it says at the point in time when the bottom of the ladder is 4 feet off the wall. Okay. So at that moment that x is 4. Now that doesn't mean x is always 4, right? Again, you have to look at the scenario and visualize the motion, understand the motion that's happening here, okay? So let's set up our old friend Pythagorean theorem again. And so we're going to go x squared plus y squared equals, and again, my ladder's not changing, so I'm just going to leave it as 8, and we have to square it, okay? So there's my Pythagorean theorem, okay? And now I'm going to take the derivative of this with respect to time. And the really nice thing with Pythagorean theorem, again, is the derivative is the same every time, right? You're going to get 2x dx dt, that's nice, plus 2y dy dt. And now here's a place you can make a real silly mistake. 8 squared is 64, right? What's the derivative of 64? It ain't 64. 0. Okay? And so, now that I have this, right, let me plug everything in. Okay, oh, I'm sorry, I'm going to make my life easier, just like last time. Pythagorean theorem, divide everything by 2. What's 0 divided by 2? It's still 0, right? Okay, now let's plug everything in. So x at this moment is 4. dx dt is what I'm solving for. Y at this moment, I don't know. So again, just like with the last question, right? You know x is 4. You can plug it into your Pythagorean theorem to solve for y. But again, just like the last question, there's a little shortcut here, right? If x is 4 and my hypotenuse, the length of the ladder is double that, it is 8, right? That should be ringing some bells. How about x root 3, 2x? Right? Special right triangles. This triangle is at 30, 60, 90 at this moment, okay? And so y at this moment is x root 3, which is 4 root 3. And dy dt, we know, is negative 2, and the derivative of 64 is 0. Okay, so I'm going to get 4 dx dt, right? This is negative 8 root 3. Bring it over to the other side. I get positive 8 root 3, right? And this is important. dx dt should be positive because this base of the ladder needs to kick out. X needs to get bigger, right? And that's why it's important to realize that dy dt had to be negative 2. So ultimately, we're going to get dx dt is 2 root 3, and the ladder was measured in feet, and we were given time in seconds. Okay. Okay, so Pythagorean theorem, related rate questions, things I want you to focus on. Okay. what is getting bigger or smaller? Which of your sides are increasing or decreasing, right? If it's something that's getting smaller, its rate of change needs to be negative, okay? And then also Pythagorean theorem questions, it's good to look at, right, what is a constant, right? And really, that's just good advice for all related rate questions, right? Label all the variables, right? Anything that could be a variable, and then look at all of them and go, which of these is important, which is not, which is constant, which is not, right? Get it down to the few things that matter, and then set up your equation, do your derivative. Okay? All right, that's all I got. And so I will see you next time.